Come on in, everybody. Whoa, that's 7 of you. We're on fire now. Bought my new Baby Yoda for nothing. Nope, excuse me. No. Anybody have any questions while we wait on the remaining people? I have to get started whether they show up or not, but anybody have any questions? All right, so last time I told you we were essentially finished with chapter 15, and we were. You basically had all the examples you needed, but I really wanted to work some more examples. So I decided tonight, instead of jumping into the elementary particles chapter, which literally we have today, and that's our only class day this week because classes are off for Wednesday, Thursday, and Friday, so you won't see me again until Monday. So because of that, I decided to go ahead and just do a couple of examples from chapter 15 to give you a better feel for what needs to be done for that chapter. Also, I did have some people from my previous class tell me that they missed test 5, which was like due on the 17th. So like totally last week. So if any of y'all did that, I was kind enough to open it back up for those viewers. So if any of y'all have that, let me know. I'll open it back up. I really shouldn't do that, but I'm trying to be nice during this quarantine situation where you're having to take an online class. That would really be a lot easier face-to-face than it is this route. So anyways, let me know. I'll be lenient this time. I'm probably going to reward the people that did it on time as opposed to punishing the people that did it late, because I want the grades to be better. So anyways, anybody have any questions about the stuff we did last time, or any homework questions, any lab questions, anything like that? I think I've said all the dates on the labs properly. Remember, your labs that you did last week are not due this week because we're not having lab this week. On my lab days are all Wednesday, Thursday, Friday. So if you're on a Wednesday, Thursday, Friday lab, which I think all of you are, then you're not going to have lab this week. So they're not due until the next lab meeting, which would be the week after. All right. Well, that being said, let's go ahead and get started. And maybe I can turn the camera off and I'll stop yawning. It does not seem to be the case. All right, I'm going to turn on my document cam, and I've taken some problems, and I just typed them out on I actually typed them out on a what do they call it, stupid thing, scratch pad or something like that, notepad, that's what they call it in the Microsoft world. So I typed it on there, and actually when you do that, it's not as wonderful as you think, because like I tried to change mu to the Greek letter mu, and it changed all of it. So evidently that kind of document has one font that it uses in its entirety. So I couldn't do that. So it's a little clumpy, but the main thing is I want you to see the words. And the main reason I did it this way is because I'm doing problems very much like problems from the end of the chapter of chapter 15. And that's what I did in my morning class. But, you know, I feel like that's probably a copyright violation. I shouldn't be doing stuff like that. So I wrote my own problems, somewhat similar, somewhat different, and obviously ugly because I wrote them in this notepad. So let me share the screen with you so you can see the problems. All right, here we go. So here's the first one. You can notice I got 3 written up here, and I use some weird notation like pi is pi, and the word lambda is lambda, that sort of thing. So 2px over lambda, yeah, that's. And actually, I miscopied that. That's actually right. It's 2px over lambda, but I had a number there that I was supposed to be putting. So let me erase that real quick. Of course, that helps you a little bit on the problem. And I'm going to say that that is 8.50x. So that's it. Okay. So a transverse traveling wave is given by d equals 0.500 times the sine of 8.50x plus 44.0 t, where d and x are measured in meters and time is in seconds. And I ask you, what is the wavelength, lambda, frequency, which I'll use the symbol F for, but I didn't need to call that, velocity, and I mean direction and magnitude, amplitude, and the maximum and minimum speeds of the string. Okay. So what we're going to do is actually calculate that. We're going to figure out what it actually turns out to be. And we're going to understand that they basically being a transverse traveling wave means that this is a solution to the wave equation. We know that the wave equation gives a solution. In this case, D, or in some cases, you might write it as X, like I did in class. X equals A cosine KX minus omega t plus 5. So I'm going to write that down, and I'm going to write this down. First, I'm going to write this down so we'll know exactly what we're using. And I'm going to write it down, and I'm not showing you that yet, because the main thing is that you can write it down from here. So I'm going to write down D is equal to 0.500 sine of 8.50 x plus 44.0 t. Okay, and what we're asked to find is the wavelength. So lambda is equal to question mark. We're asked to find the frequency. So f is equal to question mark. We're asked to find the velocity. So I'll just put v with a vector symbol over top of it equals question mark. We're asked to find the amplitude, which we called a equals question mark. And we're going to say v max slash min, and that's really the maximum velocity of any point on the string. Okay, so on the string, so the string is going to be, for instance, moving up and down as this wave passes it by, but it's very little, if any, motion to the left and right. And what we're asking is what's the maximum velocity on the string itself. So that's what we're trying to do. Now that I've written down everything, let's go back and let's show you what I wrote so you can see. I said stop share during you. Okay. So now I'm going to turn on my document cam. And you'll see D is equal to 0.500 sine 8.50 x plus 44.0 t. And I'm asked for lambda f v magnitude and direction, and that's velocity of the wave, a the amplitude, and v max min, which is the velocity of any point on the string, and they mean the minimum maximum. Now what we're comparing this to is the solution I gave you, which I think I even wrote it as x. It should have been d, because your book actually gave the wave equation in terms of d, but I think I wrote x is equal to a cosine kx minus omega t plus 5. Okay, but the reason for me showing you this problem is threefold. One, I wanted you to see what kind of problem I can give you from the wave equation. I'm not asking you to solve that differential equation, though I think you can. Hopefully you should be able to. You know, you just take the derivative twice and ignoring the other variable. So once you take the second derivative with respect to x, you're pretending 44t is just a constant. And then when you take the second derivative with respect to t, you're pretending 8.50x is just a constant. And then, of course, the second partial derivative of d with respect to x squared is equal to 1 over the velocity squared times the second partial of d with respect to time squared. So the v is what's going to turn out to be in that little spot where it says 1 over v squared. But notice here, I've got a sine instead of a cosine, but that's the second fold reason. I want you to understand that a wave is a wave is a wave. And if the wave looks like this, that's the same function more or less as a wave that looks like this. In other words, you can take cosine, which is what I gave you the solution as, and I can, for instance, subtract pi over 2 from it, and then from the actual x value. So if I just had kx and I subtracted pi over 2 from it, then that would actually start back here at negative pi over 2. So you'd see I'd get the actual sine function. So really, the thing is the same whether you use a sine or a cosine or a negative sine or a negative cosine or a cosine with plus, pi over 18, for this phi angle. This case, they actually probably found that it was a cosine of negative pi over 2. So they just changed it to sine, because whenever you have cosine of negative pi over 2, you're going to get basically sine. Okay, so that's the big thing. But what you can compare then is still the thing in the front. Remember, cosine and sine, they both wobble back and forth between +1 and -1, +1 and -1, right? So this A must be the same thing as this A. So that's still your amplitude. So we know our amplitude. We know that this is measured in meters, and sine spits out no units because it's a ratio of sides. So obviously the amplitude has to be 0.500 meters. Similarly, we know that the thing in front of the X must be the K, and the thing in front of the T must be the omega. And the plus or minus I'll deal with in a second. So these, that's two of the reasons that I showed you this. And the third reason is I wanted you to understand basically how you make that translation, not only from sine to cosine, but realizing that A is still A, and that the multiplier of X is K, and the multiplier of T is omega. And of course, what the plus or minus between them means, again, which I'll address in a second. So first off, I'm going to give you lambda. And it might be hard for you to remember what lambda is supposed to be and what, omega is supposed to be and all that stuff. But I think after studying circular motion, we already learned that omega is equal to 2 pi f. And I think that's pretty set in your head. And I think you also remember that f is equal to 1 over the period. So that's pretty well set in your head. Now, remember this. I can combine those two and say omega is equal to 2 pi over the period. And remember, the period is if you graph the wave as d versus t, the t is the minimal distance along the axis you have to go for the wave to start repeating itself. So that's helpful. That helps us understand some stuff. For starters, it tells us, how this omega is related to the period, or if we use that way, it tells us how it's related to the frequency, which we want to know. But the other thing is it helps you better understand the K, because the K is the exact analog in space, meaning K is 2 pi over the wavelength, which, remember, if you plot D versus X, since this is X here, if you plot D versus X, this lambda down here is exactly the same thing that the T is on the time axis. It's the minimal distance along the horizontal axis that you have to go before the wave starts to repeat itself. So by that symmetry, you should be able to quickly figure out, oh yeah, K is 2 pi over lambda, just like omega is 2 pi over T. So I'm going to start off with doing lambda. And of course, we say 8.50. And of course, since that's going to give out radians, this must be in radians, which isn't really a unit. You can add it in and take it out anytime you want, but it's going to be radians per meter. And that's going to be my K value, because it's the thing that's multiplying by X. But my K value is also equal to 2 pi over lambda. So I can say that lambda must be equal to 2 pi over 8.50 radians per meter. Or excuse me, let's see, K, yeah, radians per meter. Okay, so when you flip that over, obviously it's going to give you units of meters. And when I do that, I'm going to say 2 times pi 3.14159 divided by 8.5. And I get 0.739. And the next two digits are 20. And that's just plain meters is what that unit is. So there's lambda, our wavelength. So we've got our first problem solved. The first thing it asked for, we've given them. Now the next thing is the frequency. So remember, frequency is given from omega equals 2 pi f. So f would actually equal omega over 2 pi. And of course, omega is the thing that multiplies by t, so that's 44. So I'm going to say 44.0 over 2 pi. And notice this omega has to be measured in radians per second. So I'll call that radians per second. And then over 2 pi. And remember, the 2 pi really is converting radians to cycles, because there's 2 pi radians in a single cycle. So we're getting cycles per second, which you can call hertz. So I'm going to say 44 divided by parenthesis. Remember to use your parenthesis because otherwise it'll divide by 2 and then multiply by pi. So 2 times 3.14159. That gives me 7.002. 28, in fact. That's 2 extra sig figs again, and that's in units of hertz. Any questions on that? So this is what I mean by solving, in some sense, solving the wave equation. We have a generic solution that I've given you that you can obviously throw in the wave equation and see that it works. And from that, you can even find out what K is, or excuse me, what V is in terms of K and omega and phi even. And with that, then you need to be able to apply this to any situation. So if someone says this is a wave, a transverse wave, then you know, oh, it solves the wave equation. So it's sort of related to this. So you can identify the various variables. Now, velocity is a weird thing. Velocity, you remember, is F times lambda. That's the baby wave equation I told you about. But there's a smarter way to do it, because if I did this, I'm taking F, which I calculated, and I'm taking lambda, which I calculated, which gives me twice as much chance for error than calculating something from the basic quantities, right? I got an error that I got a chance that this was wrong. I got a chance that that was wrong. And then when I divide them together, I got another chance to make a mistake just in division. So it's better to use quantities we were given. So this is how I can do that. I can say velocity equals frequency times wavelength, but I realize frequency is equal to omega over 2 pi. And I realize that wavelength, of course, is 2 pi over k. Now you see the 2 pi's cancel out and you get omega over k. And that is one of the formulas for the velocity. It's called the phase velocity. Now, the phase velocity really is how fast is that little shape right here going? That's what the phase velocity is. How fast is that particular shape? Meaning you're not allowing your finger to ride across any other part of the wave. You're just taking and putting your finger down on this and riding the wave, and you're watching this whole part. How fast is that moving along? And that's what we sort of recognize as our wave velocity. So now I'm going to just take my omega, which of course is 44.0 radians per second, and I'm going to divide it by my K, which is 8.50. And that, of course, is equal to reciprocal meters. So you see a meter in the bottom of the bottom makes a meter on top. So it's going to be a meter per second, which is exactly what we expect. So I'll say 44 divided by 8.50. And I get 5.1765. 5.1765, carrying 2 extra sig figs again. And that's meters per second, which is the velocity's magnitude. Okay. Now there's a couple things going on with this question. I want to straighten something out. I didn't remember to tell my 9 o'clock, or excuse me, my 11 o'clock class this morning this part of it, but I'm going to tell you now, and of course they can see this video. The general form of this wave solution, if I use D instead of X, the general form of this wave solution is D is equal to A cosine, and then they go K dot R. Okay. That's a weird thing, right? Minus omega T plus phi. But by doing K dot R and using R as just X I hat plus Y J hat plus Z K hat, then what you get is, if this wave is going off in a direction that is along the x-axis, then you'll just get kx, which is what this is doing. If it's along the y-axis, you'll get ky. If it's along the z-axis, you'll get kz. But if it's along something else, then you'll get, kx plus another ky times y plus another k sub z times z, and that sort of thing. So it's actually more general to say k dot r, where r is just this vector here. So by realizing that that's the normal result, when you see kx, oh, it's moving along the x-axis, then it's just a matter of determining whether it's moving in the positive or negative x direction. And here's what I'm going to show you. So we have the phase, which is this entire thing right here, which of course is the 8.50x plus 44t. So if I set that equal to a constant, let's say 8.50x plus 44.0t is equal to, let's say the constant 2 pi. Okay. That means you are now looking at a very specific part of the wave. Since this wave happens to be a sine, and we're talking about it being equal to 2 pi, we're specifically looking at this little spot right there, right? And if I evaluate x in this, in other words, if I solve this for x, this will tell me where along the x-axis that dot will be at any time t later. So I'm going to solve that for x, and I'm going to get x is equal to 2 pi over 8.50. And remember, 0 is reciprocal meters, or excuse me, 8.50 is reciprocal meters, minus 44.0 radians per second over 8.50 reciprocal meters times t. Now you can already see that this is basically 2 pi over 8.50 meters. That is basically just 2 pi over the wavelength. So that's just really not the wavelength. That's 2 pi over 1 over the wavelength, which is really more like the period. So I just leave that number as what it is. So I'll say that's 2 pi over 8.50 meters minus, now 44 divided by 8 was in fact the velocity of the wave times t. So what you see is happening here is at time t equals 0, that spot, the end of that wave, is in fact 2 pi times divided by the k value, so that you get basically this number in wavelength. So it's one wavelength at t equals 0, but as t gets larger and larger, this gets smaller and smaller, and in fact becomes negative. So you see that it's actually this dot is moving to the left. So because of that, dot is moving to the negative x direction. If you do the same thing with the minus, so you have kx minus omega t, you'll get a plus here, and you'll see it's moving in the positive direction. So that's something to keep in mind. So this is also part of V. Any questions on that? Now I'm giving you that. Hopefully that explains it pretty well to you, because I know I was telling my class this morning, I had 3 semesters of this course right here, and I still didn't quite get why you put a plus there and it made it going in the negative direction, and you put a minus there and it made it go in a positive direction. I figured this out shortly into my 3rd semester. I figured out this way of thinking about it, and I've always wanted you not to, be the loser I was. So I've given you this as hopefully something that'll help you understand it a little earlier than I did. So no questions on that? So we've now got lambda, F, and V. I still need A, and I still need the V max and V min. Of course, A is just that little number in front. So I can automatically just write A is equal to 0.500 meters. And that is, in fact, the amplitude of this wave. That should be obvious. Hopefully it is to you. Did anybody not get that or not understand why that A is the amplitude? All right. Now, I also said I wanted that V max min. So V sub max / min is the maximum and minimum speed of, let's say, a molecule or a point on the string. Well, you're going to work this out in a second, but you can see right now the velocity of the wave is only 5.17 meters per second, or excuse me, just meters per second. So if you find the velocity is bigger than that, the velocity I'm getting ready to do, then you know this speed of the string is definitely going to be faster than that. And not only that, remember, this is a transverse wave, so the actual string just goes up and down. The parts of the string go up and down; they don't move left and right. So, all right. With that in mind, can anybody think? I've got sort of d, which is the same thing as x. I've got d or x as a function of time. Does anybody know what I have to do to d or x of t to get a velocity? Anyone? Yes, that's the average. But what about if I wanted the instantaneous? Jared said you could divide the x by the t, and he's exactly right. That would actually give you the average speed. But what's the fancier way of getting the speed at any instant in time? There you go, differentiate it. Okay, so in fact, you can see we're going to take d over dt, and of course that's going to be equal to 0.500. Remember, that has units of meters, and we'll leave a space here because I got to take the derivative of sine. But then the chain rule demands that I take the derivative of sine with respect to the argument and then multiply that by the derivative of the argument with respect to t in this case. So I'm leaving a space for that part. Y'all probably, hopefully, remember what it is already, but the derivative of sine is cosine. So I'm going to write cosine right here. And then I put the argument of the function, which is 8.50, and we decided that was meters to the -1 power. And you could actually write it as radians per meter. That's why its k is 2 pi over lambda. So that's x plus 44.0 radians per second on that one. I wrote the period too close to the 4. Radians per second times t. Now I got to take the derivative of this with respect to t. So I mean, in this case, since this is a function of x and t, I'm going to take the derivative of it as a partial derivative. In other words, this is like 8.57 plus 44.0 t. So when I take the derivative of that 8.57, say, is going to be the derivative of that 0. So I just get this one, which is 44.0 radians per second. And in fact, the max and min is really the amplitude, because remember, the cosine and sine functions just wobble back and forth between plus and -1. But whatever you multiply it by, then it becomes that it wobbles back and forth between. So in the sine case, it's going to wobble back and forth between V max equals positive 22.0 meters per second, because 1/2 of 44.0 is really, really easy to do. Okay, and V min is going to be negative 22.0 meters per second. Notice that is a lot higher than the wave velocity as well. So they're certainly not talking about that. Now the problem is, as we learned in kinematics, both of these have the same magnitude, so their speeds are the same. They're not really a max and a min necessarily. They're both the same size, but it's minimum in the sense that it's going in the negative direction, and a negative number is the smallest. This is the smallest negative number it will reach, and this is the largest negative number it will reach. If I asked you for the smallest speed, you'd have to say 0, because clearly this cosine goes through 0 at some point, right? Any questions on that? So that was example 1. That's a very typical problem that you're asked to do with this stuff. It's sort of just like the problem we do with the simple harmonic oscillator, except this one isn't giving us initial conditions. I could also, say, okay, my function is a cosine kx minus omega t plus phi. I could give you x at t equals 0, which you notice that's a problem because I got an x there and an x there. They're not supposed to be the same. That's why your book used the D, and that's why they're smarter than me. So anyways, and actually, you know, the real answer should probably be y, because it's a transverse wave. If it's going along the x-axis, you could treat the amplitude as the y direction. But the main point is, you can see if I gave you y equals a cosine kx minus omega t plus phi, and I said y of t equals 0 is 0, but the v at t equals 0 is 22 meters per second, right? Then you can plug in those conditions, and through that, you could actually determine phi and a. The k and the omega are supposed to come just from the wave equation when you actually take the derivative, because remember the v is k over, or excuse me, omega over k. So it's like that, except without the initial conditions part. All right, so it looks like we don't have any questions on this. I guess y'all are getting it really well. So let's go on to another question, another example, if you will. And this will be example. Guess what? I'm going with a number 2. So original as Mr. Younger. All right, first off, I'm going to go ahead and share my screen again. So I'm going to share it with this question right here with you. It says, what is the frequency f of a standing wave on a string if the string has, that's supposed to be antinodes. I don't know where that came in. That must have been one of those times I hit Control Z. Nodes. If it has n antinodes, a length L, a mass per unit length mu, this is one of those cases where I couldn't type the Greek letter mu, and a tension F sub T. This is one of those cases where I couldn't type subscript. So what I'm going to do right now is record that information. So I've got the frequency is F, and that's what we want to know. So I'm going to say F is equal to question mark. Number of antinodes. We don't, or you might not necessarily know what that means right now. So I'm going to just write number of antinodes equals n, and I'll talk about that in a second. We have a length of string L, and we have a mass per unit length mu, and we have a tension F sub T. In other words, we're pretending we know all these things except for F, and we want to solve for F. Okay, so I've written all that stuff down. Do you all understand the question? I'm asking for what frequency would occur for a standing wave. So this is very much like a wave that you would pluck on your guitar or banjo or violin or whatever. It's a standing wave, and that's what we create when we pluck them. So let me stop sharing for a second. All right, so you see I wrote F. The number of is question mark. The number of antinodes is n. The length is L. The mass per unit length is mu, and the tension is F sub T. So first off, I want to examine a mass on a string in tension. So when you're just looking at a string, it looks like that. But when you pluck it, it can do a couple things. So if you pluck it one way, meaning you're basically forcing a wave on it that has just the right parameters, then it'll look like that. And what happens is you sort of gave this end a shake, is one way of thinking about it, by plucking it. And that created a wave like this. And just as this part of the wave got to this end, this part of the wave got to this end. Now, when that happened, because this is a fixed spot, it's a node. The fixed spots are called nodes. And dead center between them is called the antinode. So this one, in fact, has one antinode. Okay. Now, as soon as it gets to this end, it's going to yank up on that hook or whatever's holding it in place. That hook or whatever's going to hold it in place is going to force the wave to turn upside down, and slowly it's going to come back and do this. Now, at the instant this happens, then you're adding this wave and that wave, and they shrink down to the zero wave because the trough, the crest is lining up with the crest, which is actually a trough in this case because it's upside down. So you get zero. And it just does that back and forth. So you see it going boom, 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 boom between these two states. Now, if you pluck it with a slightly different, or if you shake it, say, with a higher frequency, then you get a slightly different waveform. In fact, what you get is this. And notice this is that same wave, but the instant that spot got here, that spot got here, and this spot got here. Now it's going to turn upside down and run back the other way. And when they're just like that, they're going to collapse to zero. And then another one will come, and then another one will bounce back, collapse to zero, another one will come, another one backs back. That is what a standing wave is. It's these waves that go back and forth, but they meet at just the right time where they constructively interfere, destructively interfere, constructively interfere, destructively interfere. This one has how many nodes? How many antinodes? So remember, antinodes are the shaking part. So there's 1, 2 here. Now in this scenario, the length of the string is, I use the script L. So the length of the string is that length L. And from this, you can see L is equal to lambda over 1/2. Remember, this represents a whole wavelength. I just did that much, so that's a half a wavelength. In this case, L is equal to a whole wavelength, lambda. If I try another one, this is called the fundamental frequency. It's also called the first harmonic. This one's called the second harmonic, or the first overtone. Okay, now we're going to do another one. And of course, the string initially is just at rest, but you start shaking it like you're supposed to. And in this case, you're going to get half a wave, another half a wave, and then another half a wave. So this is 3 antinodes, which I'll just write AN now. And that is L is equal to 3 lambda over 2. Of course, the next one would be 4 antinodes, and that would be 2 wavelengths. If you're looking at these, you can see this could be 1 lambda over 2. This could be 2 lambda over 2. This could be 3 lambda over 2. In fact, if you continue on, L will actually equal N lambda over 2, where N is the number of antinodes. Okay. So if that's L, then lambda has to be equal to 2L over N. We also know the velocity of a wave is equal to frequency times wavelength. And we also know the velocity of the wave is equal to the square root of the tension divided by the mass per unit length, which again, we were told we know. So we're saying Ft is the tension, mu is the mass per unit length. So I've got all this, and they asked me to solve for the frequency. So I know all I got to do is say frequency is equal to 1 over lambda times the square root of the tension over mu. Well, 1 over lambda is just going to be 2 over n times lambda. So I'm going to say 2 over n times lambda times the square root of Ft over mu. So if I actually want the friction or the frequency of this, that's our value. And if you look, your book has one where they ask you to prove what the frequency is, and that's more or less the same type of problem. I just asked you to find what it is, but that's the same thing. Any questions on that? And notice when you do, for instance, pluck a stringed instrument, this is probably the tone you hear most. But notice this one, when I go to n equal 2, I go from 2/1 to 2/2. So that's half the frequency it was before. And then when I go to 2/3, then it's a third of the frequency. So those all are harmonics with each other. And that means they harmonize. So they sound okay together. That's why it's perfectly okay to get multiple vibrations on one, because the frequencies are going to be multiples of basically a ratio. So any questions on that? So that was question 2. I like that one. We're going to do another one now, though, and this one's going to be where we have a little oscillator. So we have this little thing that one way you can think of it is it would be like inside of a car speaker. You'll look, there's this little diaphragm, and if you opened it up, you'd see on the back there's a magnet. And then there's a magnet, or at least a piece of iron, on the back of the diaphragm. And when current goes through the big magnet, it attracts that magnet or that piece of metal in the back of the diaphragm. So the diaphragm is just going up and down, up and down, up and down like that. Well, if you connect something to that metal and put that tie a string to it, then that diaphragm going up and down is going to cause the string to go up and down. And if you put a 60 hertz signal in there, then it's going to go up and down with a frequency of 60 hertz. So in this problem, let me share screen again. We're going to consider a situation like that. A string is connected to a F equals 120 hertz oscillator and run horizontally over a pulley to a mass M hanging from it. If the mass per unit length of the string is 9 times 10 to the -4 kilograms per meter, and the length between the node near the oscillator and the node at the top of the pulley is L equals 3 meters, what is the required mass for the following number of antinodes? So I'm trying to put this in a little neater form instead of the sneeze that this program did. Now let's see if I can. Whoa, no. Ah, darn it. Stupid son of a. Okay. So anyways, that's what we're doing. So I got F equals 120. So this is example 3. I got F is equal to 120 hertz. I'll take that as 3 sig figs. I got L is equal to 3.00 meters. And I've got mu is equal to 9.00 times 10 to the -4 kilograms per meter. Now, your book used the term linear density. This is another reason why I solve problems like this, so you can get an idea that what words like that mean. I actually used something similar to linear density when we were integrating to find, for instance, the center of mass or the moment of inertia of certain objects that were linear, that were basically one-dimensional. So it's the same sort of thing, but it's the mass per unit length. And you get that here. And then I was told that for N, which we've already established, N is the number of antinodes like we did in the last example. So we want for N equal 1, N equal 2, N equal 5, and just plain N. Okay. So I've written all the information down. I think I've got everything 3 meters. So now what I'm going to do is stop sharing and draw the picture so you can make some sense of what I'm talking about. So the picture is this. We basically have this little oscillator thing, which looks like this. Okay, so that thing can go up and down, up and down, up and down, because it's got a magnet back here. When it goes up and down, of course, that means it makes this waddle. And in fact, right about here will be a node. This part's actually an antinode, but it's really, really close to this. But so ideally what you want to measure is this spot that's not moving to this spot that's not moving, which might be a little bit further to the left than actually on top of it. But that's the actual L that we're talking about, from there to there. Now a mass is hanging on it, of mass M, And that means basically that the tension force is just M times G. Right? So we've already learned that when N equals 1, L equals lambda over 2. Remember, that was the problem I just worked out for you. In other words, this length from here to here is half a wavelength. And of course, that means lambda is equal to 2L. When N equals 2, then L is equal to 2 lambda over 2. So that means lambda is just equal to L. And when N equals 5, then I think you know that L will equal 5 lambda over 2. So so lambda is going to equal 2/5 lambda. And in fact, for N equal N, we're going to get basically lambda equals 2 lambda over N. Okay, so I'm just sort of going through that same process. Okay, when I have a single loop, that's lambda over 2. When I have 2 loops, and that's just plain lambda. When I have 3 loops, it's 3 lambda over 2. I didn't write that one. 4 loops, it's 4 lambda over 2. And then 5 loops is 5 lambda over 2. So it's 2.5 wavelengths, basically. Now that we got that, we know that V is equal to the square root of Ft over mu. We know that Ft is mg, and we know that V is equal to F times lambda. So for part A, N equals 1, then we've got the square root of mg. Notice I just replaced the tension with mg, divided by mu is equal to F, which we're given 120 hertz, times lambda, but we found, in fact, lambda is 2L here. So if I square both sides, I get mg over mu is equal to 4L squared F squared. So M is going to be 4 mu L squared F squared over G. So in calculating that, I'm going to say 4 times 3 squared times 120 squared. And then I'm going to divide all that by 9.8. So I get 52.898. And that should come out in kilograms. And that's the mass that I need to hang. 52 kilograms is pretty big. That's 110 pounds, right? And that's mainly, you can see, because I use such a long string. We don't use too many instruments that have strings 6 foot long, right? Actually, 3 meters. That's more like 9 feet long. Oof, yeah, we don't use any of those. All right. So that's the first case. Now for the case of N equal 2, we found that lambda is just equal to L. So in this case, we got the square root of mg over mu is equal to F times just plain L. So this gives us mg over mu is equal to F squared L squared, or finally we can say M is equal to mu L squared F squared over G. You can see basically it's the same number, but we're going to divide it by 4 now. So I'll say divided by 4 because I'm lazy, and I get 13.224 kilograms. And obviously that's 2 extra sig figs. Any questions on that? Let's try N equal 5. For N equals 5, we get square root mg over mu is equal to, in this case, we found 2/5 lambda. So it's F times 2/5 times, or excuse me, 2/5 L. I don't know why I wrote it that way. I actually wrote a lambda over here and lambda over here. So this should actually be a L and this should actually be an L. That's 2/5 L. So again, we can square it. We get mg over mu is equal to L squared F squared. In this case, we got 4L squared over 25. So m is going to be equal to 4 mu L squared F squared over 25g. So that's a little bit more complicated than the one we did before, where we just had where we just had 4 mu L squared over that. So basically, if I take that original number and divide it by 25, I can get it. So I'm going to do that because, again, I'm lazy. Let's say enter, divided by 25, and I get 2.1160, 2.1159 kilograms. So you can see the kilograms are actually getting smaller. And of course, you might want to go ahead and have a general formula for any number of antinodes n, and that's why we did the n case. So in the n case, basically all I got to do is plug this in. So I'm going to say mg over mu square root is equal to F times, in this case, it's 2L over n. So we can square both sides. We'll get mg over mu is equal to 4 L squared F squared over n squared. And finally, that gives us m should equal 4 mu L squared F squared over n squared g. So that's the formal derivation, if you will, of the mass required to make a given 120 frequency wave that has a certain length or a certain number of antinodes, whichever you want. Does that seem pretty clear to you guys? No questions on that? All right, so those are some of the types of problems I expect you to solve. Another one that I liked, and I sort of did this for you in class by drawing the two waves right over top of each other, and then tried to draw lines to connect the different points or something like that. But your book has a really nice problem. I like it. The problem number, I'll show it to you when I do the share screen. So I'm going to share a screen and show you a page out of G.M. Coley's textbook, which is copyrighted, of course, and it's a good textbook. He's getting ready to release his new edition. We're going to switch to that 2 semesters from now. But right here, it's number 90. It says 2 wave pulses are traveling in opposite directions with the same speed, 7.0 centimeters per second, as shown in this figure. At t equals 0, the leading edges of the 2 pulses are 15 centimeters apart, 5, 10, 15. So you see after 1 second, this one's going to have moved 7 centimeters. This one's going to have moved 7 centimeters. So they'll be 1 centimeter apart after 1 second. After 2 seconds, then this one's going to have moved 14, and this one's going to have moved 14. And of course, they were only 15 apart. So 15 minus 28 is what, 21, 22 or something like that. And what you're going to see is bit by bit, these little parts add up directly over top of each other. So one of the ways you could do it is actually create a Excel spreadsheet and just use part of the sine curve, or you can just pick values that look reasonable for X and Y, or for X and Y, and then slowly let them converge and let Excel do the work for you. But I do recommend you doing this at least by paper and pencil once. Just drawing this directly over top of this. Make sure the two have different widths so you can actually see what's going on. You might consider a point in time when this edge and this edge are lined up, so you can see how it adds right on this part. You also want to consider a point in time where this center and this center are lined up, and you want to definitely choose maybe two waves of the same height like this one, but one that's, significantly narrower than the other. This one's only half as wide as that one. I would even say maybe a third as wide or even a quarter as wide would be more interesting, because you're going to see this thing with just a wave on top of it in some sense moving across here. So that's something I do recommend you do just for fun of it. This is that generalization I was telling you about, K dot R as opposed to K dot or K times X. So they're showing you that. That's not really anything that big of a deal, but I just thought I'd mention it to you while you're here. Let's look at some other stuff. Let's see if there's anything else that jumps out at me that I wanted to do for you guys. Does anybody have any questions you run into that you'd like help with? There's a good question. Number 76. A guitar string is supposed to vibrate at 247, but it actually vibrates at 255. By what percentage should the tension of the string be altered? I'm going to work a different problem, but a similar problem, because I'm pretty sure people use these problems for homework. 76 is an even problem, so those are ones that instructors like to actually assign, because the answers are not in the back of the book for those, and then they can grade them. So I don't want to solve a problem like that. I'm going to say, in fact, instead of 247, let's say a banjo string have a banjo, so it's nice to use that from time to time. Plus I know the notes on the banjo string, when it's properly tuned, I know them, I know what their frequencies are and that kind of stuff. And not only that, I have this little tool that allows me to see that. So let's kill this for a second. I'm going to stop sharing. And I have, for instance, I said stop sharing it. And I have this app that actually allows me to see exactly what frequencies they are. And then when I pluck my strings, it'll play what frequency I'm making it at, like it's picking up my voice right now. One of my strings, for instance, is supposed to be at 146.87 hertz. Let's say a banjo string is playing at F is equal to, instead of 146.87, let's say it's playing at 158.0 hertz instead of the tuned F equals 146.87. When we get into, or if you read the sound section, which we skip, obviously, you'll actually see that when you play two strings that are near each other, like let's say, or play two instruments that are near each other and they're both supposed to be playing the same beats, what happens is that superposition principle comes into play, and you have sine kx minus omega t plus sine kx minus omega t, but the two k's and omegas are different. So it's k1x minus omega 1t and k2x minus omega 2t, right? Well, it turns out if you actually add those and then use your trig identities, what you'll end up getting is you get a product of like sines and cosines, and one of them happens to be the average of the two frequencies, and the other one happens to be the difference of the two frequencies. And that difference is what you hear when you realize your instrument's not tuned. You hear a wah, 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 wah. That's called the beat frequency. So that's something neat to think about. I'll just say that's the beat frequency. But that's how we use our ears to tell whether or not something is properly tuned. So what I want to know is what percent change in tension will fix the problem. So let's think about this a little bit. This is actually why I sing at music. I think about it too much, as you're going to see in a second. But anyways, what percentage change in the tension will actually fix the problem? So what we know is velocity is equal to the square root of, like your book uses, the tension force divided by mass per unit length. If you're talking about a certain string, then the mu is fixed. If you look at, for instance, my banjo or a guitar or a violin, you'll see that different strings have different thicknesses, and that's different mass per unit length. So that's a parameter you can't really fix. You also know that if you have the if you're not adjusting the tension in the string, then the velocity remains constant. And since velocity is equal to frequency times wavelength, that means frequency is inversely related to wavelength. So if the frequency goes up by 4, say, then the wavelength is going to go down by 4, multiplicative wise. So like if you went from 100 hertz to 400 hertz, then your wavelength might go from 4 meters to 1 meter. Okay, so that's the two things that are going on here. But what we know is the frequency is what? Is the frequency too high or too low? Is strings frequency too high or too low? That's the first question you want to satisfy. You want to be able to answer so that you can satisfactorily solve this. So we're saying the string is playing at 158 hertz, but it's supposed to play at 146. So the frequency is too what? Y'all can type it if you're nervous. Yes, Jared said high. Yes, the frequency is too high. So in order to decrease the frequency, should I loosen or tighten the string? And loosen or tighten just means decrease or increase the tension in that order. Yes, we want to loosen it, because if the tension goes down, the velocity will go down. And of course, for a given string, the length from the nut to the bridge is the multiple of the wavelength that you're dealing with. So this, for a given string, this lambda doesn't change until you fret it. You're playing it ostensibly not fretted, so that lambda doesn't change. So since velocity is directly related to frequency, thumbs up, and the frequency is too high, you want to, in fact, lower the frequency. So yes, the answer is too high and loosen. Okay. So what we want is we want the frequency to be, well, let's say the velocities are going to be, the wavelengths are going to be the same. So we'll say square root of the tension over mu in case 1 is equal to the velocity, is equal to the frequency in case 1 times lambda, and the square root of the frequency in case 2, and I shouldn't subscript the mu at all, I'm just going to subscript the F tension. That quantity is going to be equal to F2 times lambda. And again, since the lambda is the same, we can say that square root F tension 1 over square root mu over F1 is equal to square root F tension 2 over square root mu times F2. So that's a relationship that we can make. We in fact want F2 to be 146.8 hertz, and we know F1 is in fact equal to 158.0 hertz. And we need to figure out how much the tension is going to change. So if I square both sides of this, notice the mu's cancel out. I don't need those anywhere. I can just say F tension 1 over F1 squared is equal to F tension 2 over F2 squared. So since the F1 is the bigger one, I'll put it on top. So I'll say F tension 1 over F tension 2 is equal to F1 over F2 squared. So I now have the ability to calculate the ratios, the tensions. The tension 1, or excuse me, the friction, excuse me, the frequency 1 is 158.0 hertz, and the frequency 2 is 146.8 hertz. And then of course we got to square that. So I can say 158 divided by 146.8, and then I'll square that, and I get 1.1584. No units. Okay, so what we're saying is we need the second tension to be loosened by FT2 is equal to basically F tension 1 divided by 1.1584. Okay, now you could also do some math with that and figure out the difference, because what they want is the percent change, and that means the difference divided by the original quantity. So the percent change, which I'll write like this, percent delta, is like FT1 minus FT2 over FT1. That's really what it is. Of course, you got to move the decimal 2 places to the right to get that. With this equation right here, you can in principle figure out what FT1 minus FT2 is, but this would be more than enough for me. I would just say I'm going to reduce the tension by dividing it by a factor of 1.1584. But that's a possibility. Anyone have any questions on that? Let me go ahead and sort of finish this out. I was hoping I could get it all in that one page, but it's not going to happen that way. So what I'm going to do is I'm going to move this tablet down a little bit, this notepad down a little bit, and I'm going to take this expression right here and say FT1 is equal to 1.1584. Okay, I'm okay on time, times FT2. And then I'd say, okay, well, FT1 minus FT2 should be equal to 1.1584 FT2 minus FT2. So you can see basically I'm just going to subtract the 1 and I will get 0.1584 times FT2 is equal to FT1 minus FT2. So now I can say delta F over FT1 is equal to 0.1584 FT2 divided by FT1. And we already know how to put that in. So now I'm going to say the percent difference, which is the same thing I said earlier as delta, percent delta or whatever. Okay, all I have to do with that is put this over this and move the decimal to 2 places to the right to make it into a percent. So I'm going to replace FT1 with that quantity. It's going to be 0.1584 FT2 over 1.1584 FT2. So you see the FT2s cancel out, and I'm going to get point let's divide that by And this gives me 0.1367 is the difference. So I think I have to change it by 13.67%. So a lot of this stuff is more about the algebra and knowing the arithmetic and knowing the what they mean by percent differences and stuff like that. Notice most of the work was done in me trying to figure out a way to do a difference of two quantities that I didn't know either one, right? But that should get it 13.67% decrease is what we have to do it. Any questions on that one? All right, so I got like 5 minutes left, so let me show you something. I'm going to turn it back to, whoa, not that. So for instance, this is my banjo, and you can see it's not, the camera's not that great to pick up the individual strings. Probably the only string you see is that one right there. And the reason you see that one is because that's the fattest string, and the fattest string is actually going to pay, as you might have suspected, since frequency times wavelength is inversely proportional to the square root of the mass per unit length. You would probably think this is going to be a lower frequency, and it is. Here's another string. This is the drone string. That's the thinnest one on here, and it's actually a little bit short, but you can hear that's a much higher pitch, right? So when you go to, for instance, adjust the tuning on something, then you got to think, okay, is that too high or too low? And let's say it's too high. Well, if it's too high, then I need the frequency to increase, or excuse me, the frequency to decrease. And to decrease the frequency, I've got to decrease the velocity, which means I'd have to loosen this bolt right here, which adjusts that string to make it looser, okay, or more loose. Additionally, if I'm playing an instrument, especially one that's not fretted, it's nice to have a fretted instrument, because wherever I put my finger, that makes the string the length from this fret to the bridge. When it's unfretted, though, of course, the string length is from the bridge to what we call the nut, which is that part right there. So you have for each of those a fixed note. You have a fixed note for the fundamental frequency, and that fundamental frequency has to be, of course, half the wavelength. So the wavelength of this particular string when it's played is twice as long as this. If I find that I'm playing an unfretted instrument and my pitch is too high, meaning it sounds like it's too pingy and less deep, then I need to lower my frequency. But I can't really easily do that. I can't adjust the tension in the middle of my playing. But since the velocity is set on the wave, the velocity is set. Once you have adjusted this and leave it alone, the velocity of the wave is set. So that means F times lambda has to equal a constant. If I want my F to go down, then I better make my wavelength go up. So if my finger was, say, here, and I wanted a higher pitch noise, that's a higher frequency, then I would want a lower wavelength, so I'd move it here. If my finger was here and I wanted a deeper pitch noise, that means a lower frequency, then I need a higher wavelength, and I'd move my finger back. And this makes you a very horrible musician. This means you're going to think that to death, or at least I do, and there's going to be, you know, maybe a 30-second wait between consecutive pluckings. So I don't recommend doing it, but it is interesting that you can get back to all this stuff just from using the simple wave mechanics that we're learning right now in chapters 14 and 15. So that's it, guys. We are done. You guys can have a happy Thanksgiving. And remember, we do not meet again until Monday. I don't have any labs except for Wednesday, Thursday, and Friday, so I don't do any labs this week at all. Hopefully you are as lucky as me. Beyond that, I hope you have a wonderful holiday, and make sure you let me know if you did miss a test I wish I could play out. Luckily, I don't have my banjo strings plucker, so I usually play some opening of that song on Deliverance. That's my funny go-to song. But anyways, no, I can't do any of that right now because I'm completely out of practice. I would otherwise love to play for y'all. All right.
Happy Thanksgiving.
Have a good one, Mario. Like I said, I'll wait around for the last person to ask any questions. If y'all did miss a test, let me know so I can give you a chance to do it. All right, looks like everybody's gone but Mario. Did you have a question, Mario, or are you just not logged out, bud?
I was just double checking to make sure. I thought I'll make sure I got all the tests in. I think I did.
There was one that was supposed to be due like on the 17th. That's why it surprised me. A student asked me about it today because that was, quite a few days ago, 5 days ago. But anyways,
was that the 10, 11, and 36?
Yeah, that was test 5.
Okay, yes, I did it. Okay.
Well, have a good one, sir.
Okay, all right, thank you.
Bye-bye.
All right.